Our next speaker is Professor Carla Gomez, who's Professor of Computer Science at Cornell University. And Carla is going to, in her pre-recorded talk, talk to us about artificial intelligence for accelerating materials discovery. So very much looking forward to her talk. So if we could go to Carla's talk, please.
Hello, I'm Carla Gomes. I'm a professor of computer science at Cornell University. And today I'm going to talk about artificial intelligence, AI, for accelerating materials discovery. These are exciting times for AI. AI is radically and rapidly transforming our daily lives and business, moving from the academic world to the real world. AI is producing intelligent autonomous systems, and now we have, for example, Google Translator, virtual personal assistants, fully autonomous trading systems, and self-driving cars or autonomous drones and assistive robots are also becoming a reality. All this has been enabled by a qualitative change in the field, in part driven by what we call big data and also deep learning, but also many other cumulative AI developments. So what's the next frontier for AI? Well, I believe scientific discovery is now the big challenge, and that's exactly why I've been highly engaged in research concerning materials discovery. Today, I'm going to talk about AI for accelerating high-throughput materials discovery, and in particular, I'm going to talk about a very challenging problem, the crystal structure phase mapping problem. So let me start by acknowledging my students and collaborators. So at the top, you have my lab, my students in computer science. And of course, I'm a computer science, so I really need to collaborate. And I have wonderful collaborators in material science. I've collaborated with Bruce Vandover, who is at Cornell, and John Gregoire, who is at Caltech for several years, and also with Holger Stern, a postdoc at Caltech, and Santosh Saram, who used to be at Caltech, and now he's at Toyota. So I'll start by giving you the big picture about high-throughput experiments, and in particular, crystal structure mapping. So, material science can now synthesize thousands of materials simultaneously. They use a technique called co-sputtering, which is similar to atomic spray painting. And you see here an apparatus where they have three guns that can depose three metals onto a silicon wafer. So they can synthesize thousands of materials a day, and using the X-ray diffraction, they can now characterize also, hundreds and thousands of materials a day. Well, the bottleneck and the challenge is how to infer the crystal structure of the materials based on the X-ray diffraction patterns. And this task is really challenging from a computational point of view. Here, what we see a ternary representation of the deposition space. We have, three metals, and each point corresponds to an X-ray diffraction pattern. And what we would like to do is, based on the X-ray diffraction patterns, we would like to infer the crystal structure of the materials. For example, here we have different phases. And for example, here, this particular phase is an FCC crystal structure. This problem is very challenging because we can have pure phases, but also mixed crystal structures. So a mixture of crystal structured, and it is very challenging to mix this the X-ray diffraction patterns, and therefore, material science can only analyze a few systems a year. So more formally, the crystal phase map identification problem can be defined as we are given as input a collection of X-ray diffraction patterns. We also are given additional physical constraints, for example, phase connectivity, Gibbs rule, etc. And what we would like to do is we would like to output the M phase regions, some of them pure regions, others mixed regions. Each region corresponds to a mixture or a pure crystal structure or mixtures of crystal structures. And we would like to get also the X-ray diffraction pattern that characterizes these phases. Why is this problem so challenging? Well, this problem is quite challenging because this is what we call unsupervised learning as opposed to supervised learning. In supervised learning, we are given what we call labeled data or lots of examples, but here we don't have that. In fact, the big success of machine learning really has depended largely on big data and large amounts of labeled data. The reason now it's so easy to, identify faces or objects in an image is because, machines have been training by seeing, a million cats, so it becomes very easy to identify and recognize a cat or a car or a person. Well, in scientific discovery, we don't have that. We don't have lots and lots of examples. And in fact, we also have to deal with noise, incomplete data, and uncertainty. So, as I mentioned before, standard machine learning techniques fail to actually solve this problem because it's hard to capture the underlying physics of the phenomenon. And for that, we require a rich set of combinatorial constraints to capture the physics of the phenomena. And this is exactly what we have been pursuing in my lab, a synthesis of machine learning techniques with constraint and probabilistic reasoning, sampling, and optimization techniques. So, in case you may think this problem is unique, actually this problem is a particular case of a general problem that we refer to as pattern or factor decomposition or source separation. And here I show several examples. I show the phase map identification problem that I just talked about, but also other problems such as flight call detection for bird conservation or elephant call detection. From both problems, we want to identify flight calls or elephant calls from audio recordings, or music source separation, where we may want to identify single instruments from a song. Or even another problem is what we call topic modeling, where given a set of documents, we want to identify the key topics that are present in the collection of articles. So this is often solved as a pattern decomposition problem or a matrix factorization problem. In fact, other research have used this approach for the crystal structure phase map problem. Well, so how do we formulate this problem? We are given a collection of documents or a collection of X-ray diffraction patterns, and now we want to decompose this matrix A into two matrices, a matrix W that contains what we call the basis vectors, or basically the vectors that encode pure crystal structure or pure topics in documents, and another matrix H that we call the activation matrix, basically that contains the list of topics of pure crystal structures presented in each sample. Well, what makes this problem very challenging is that, we want to make sure that our pure crystal structures obey the laws of physics. So we need to consider shifts, Gibbs rules, etc. And this is exactly why this problem is so hard. And in particular, we want to make sure that the basis vectors that we produce, the pure crystal structures, are meaningful from a physics point of view. Here is an example where, we have all these red points that correspond to XRD measurements. And you see here they are stacked. The spectrograms are stacked. And this particular point, I'm going to explain this point using, two pure crystal structures or basis vectors. And you see the weights of each crystal structure. Well, we have been working on this problem for a while. In fact, we initially formulated it, rigorously as a computer science problem, as a pattern decomposition problem in machine learning. We developed several techniques based on what we call satisfiability modules theory to solve these problems. Here we assumed that we would have, very clean spectrograms, which that's not the case. And therefore we develop other methods to further, scale up solutions, including what we call human computation and parallel computing for embedding, human input to analyze these patterns. So here I show a visualization of, again, a collection of XRD measurements. This particular point A corresponds to this line, and here we have the spectrogram, and here we have a heat map where all the spectrograms are represented with the intensity in terms of different colors, and they are stacked. And, we discovered that these heat maps are good for human input. In fact, here you have an example where we show this pattern to actually high school students, and even we put this on Mechanical Turk, and the participants could clearly see that even though these little points were, the algorithm thinks these are peaks, well, the humans could easily see this is just noise and ignore the noise, and they could easily identify a pattern here. As an aside, we are actually developing fast algorithms for background subtraction, and these algorithms are actually outperforming other algorithms and work very well for Raman data too. So here is the pattern identified by human participants. And these were high school students or actually participants on Mechanical Turk without any material science background. So we have also made available data sets with benchmark problems, and we developed also other techniques combining, for example, constraint propagation with mixed integer programming. And more recently, we developed the techniques, relaxation and projection methods for fast constraint matrix factorization problems. We have also developed FaseMapper. FaseMapper is an AI interface and platform that integrates a variety of AI solvers and allowing for rapid solution updates. So, FaseMapper and our AI solvers led to the discovery of a new family of solar light absorbers by our collaborations at Caltech. And also, so this was featured in a cover article of the ACS Combinatorial Science, and also a cover article of the AI magazine. And we actually also received an Innovative AI Award for this work. Well, I'm not a material science, so I thought I would show a video. This was, our colleagues and collaborators, John Gregoire and Santosh, show how they use PhaseMapper for materials discovery.
Hi, I'm John Gregoire. Santosh Suram and I are researchers at the Joint Center for Artificial Photosynthesis, and we're going to show you how we use PhaseMapper to help us discover materials at JCAP. We'll focus on a recent example of a discovery of a new light absorber material. A critical parameter of light absorbers is the band gap energy, which determines the portion of the solar spectrum we're able to absorb. And we make libraries containing lots of new materials that have never been synthesized before using a technique called co-sputtering. And we get these libraries of materials where there's all different combinations of different elements from the periodic table, in this case niobium, vanadium, and manganese. We have instruments that can measure their optical properties to determine that critical band gap energy, and an example of this library is shown here, where there's lots of interesting trends in the band gap energy and lots of materials that have a band gap near the 2 eV range that we're interested in for this application. Our issue for a couple years was being able to understand what is unique about these materials that gives rise to the desirable band gap. To help us understand this, we used synchrotron X-ray diffraction, which we perform at SSRL, to create a library of XRD patterns. These are fingerprints for the phase of the material at all of these different compositions. Using PhaseMapper, we were able to combine the state-of-the-art solvers with our expert knowledge of this data set to create the solutions that had evaded us for years. And Santosh will provide a short demonstration of how we did this in PhaseMapper.
The 317 compositions at which XRD spectra were acquired are shown here. The PhaseMapper tool allows us to slice compositions along any orientation and visualize compositional variation of XRD spectra as a heat map, with options to emphasize major peaks and minor peaks. These slices can be expanded or narrowed for representative sample selection. The PhaseMapper is used to optimize over 30,000 matrix elements. The heat map visualization shown earlier enables the expert user to provide reasonable estimates for the number of phases, number of shifts, and a runtime of 5 seconds is typical to obtain an initial solution which can be improved by adding expert constraints. The solution obtained can be saved and is automatically loaded for visualizations such as sample-specific reconstruction. This allows rapid inspection of reconstruction quality at several compositions. The plot on the left shows the spectra of the phases obtained. The plot on the right maps phase concentrations using point sizes. The shift parameter is mapped using color, allowing us to capture phase maps and identify compositional changes in lattice parameter. The matching of the phase spectra with standard spectra can be visualized using shifting, scaling, and broadening operations. This operation can be repeated for all the expert-provided standard solutions, and any standard pattern can then be frozen to rerun the solver to provide a more optimal solution. Having all the functionality available in the web app with algorithms that run within a minute allow us to generate phase maps during experiments at SSRL, which is greatly enhancing our productivity.
The PhaseMapper solution allowed us to identify the phases of interest as light absorbers, and we're looking at just one of those phases here. And something we had not realized before is that sometimes the shift parameter of this phase does not change with composition, and sometimes it does, which when we combined that with our band gap information, made us realize that by changing the composition in the shift parameter, we can control the band gap energy of these light absorbers. Having this level of control in metal oxide light absorbers is really rare and a discovery that was uniquely enabled by PhaseMapper. So we are very thankful to the developers of PhaseMapper and for this unique collaboration that has enabled the discovery of promising energy materials.
Well, let me now wrap up, and I will briefly talk about Sarah. Sarah is an AFO Samuri launched in February 2018, and Sarah stands for Scientific Autonomous Reason Agent, and the idea is to bring together materials experiment theory and computation to advance scientific discovery in materials discovery. So this is a large team, again, a team of material science and computer science. Bruce Vandover, Mike Thompson, Chris Wolverton, John Gregoire, and Alex Zanger are material science, and myself and Bart Selmer are computer scientists. And together we are interested in, accelerating discovery in materials discovery. So Sarah will integrate material science and computer science to accelerate the discovery and development of new materials, from identifying, new candidate materials to guiding their characterization and synthesis. So essentially, Sarah is a multi-agent system that will drive synchrotron characterization, laser spike annealing, and DFT calculations. So the big picture is to encapsulate the scientific method for materials discovery in Sarah. So Sarah will be able to formulate hypotheses by performing database mining and hypothesis generation. But Sarah will also be able to plan and design experiments and, of course, analyze the experiments, in particular phase mapping and knowledge discovery. And this will include on-the-fly DFT. And to do that, Sarah will be equipped with a variety of AI techniques, AI planning, constraint reasoning, auto optimization, data mining, machine learning, and active learning to design and plan the experiments, and also human-computer interaction. I want to wrap up by going back to a slide that I showed before, where basically I show that materials discovery is just a particular case of a general class of problems called source separation problems, of pattern decomposition problems. And actually, often we refer to these problems as these cross-cutting computational themes as subway lines. And in fact, here I'm representing this subway line as a blue line. And you see here that we are, in addition to working on this particular problem, we are working on many other problems. And in fact, this is part of our philosophy. The students should work on similar computational problems in different domains. And therefore, these students that you see here are actually working on materials discovery, but also on the elephant and the flight call problem and the eelgrass problem. I didn't talk much about it, or even music. So this is actually part of a major effort. In fact, my research, I have been passionate about a new field, the field of computational sustainability. And the big picture is to develop and apply computational techniques to address the key challenge that we face today concerning sustainability issues. So I talked about this pattern decomposition in big data problem, but we are actually also tackling many other challenging problems concerning sustainability. Thank you.
Great. Thanks again, Carla. That was a wonderful talk. We're back live with the webinar, Machine Learning, Artificial Intelligence, and Data-Driven Materials Development and Design. I'm still Benji Mauriyama at the Air Force Research Lab, here with our participants. So that was Professor Carla Gomez at Cornell University. We also have Chris Reyes from Buffalo and Jay Hatrick Simpers from NIST. Also like to thank all of the people who've connected on. We've had a tremendous response in this webinar. So I think right now we have over 200 people who are connected in, and that's a great participation. So Carla, this question is for you from Petko Bogdanov. How do you combine simulation data and observational data? How do you assign certainty in an ML model if we combine both?
So I would say this is actually an excellent question. And in fact, as I mentioned in my talk, one of the key challenges that we have here when it comes to, material science is, for example, the problem I described is the fact that we don't have a lot of examples. We may have a lot of data, but we don't have what we call examples, data with labels. And therefore, it is important to actually find ways of generating those data. And that's where simulate data can play a key role. In fact, we are using approaches like that, where we use, simulated data or data based on theoretical knowledge, and we can actually, in fact, we are working on a technique that we call imitation refinement. That is really use those data to train our models. Of course, as Peter, if I recall his name, or raised, one issue is that often we were training our models on very clean data, with theoretical data. Therefore, we need to compensate for that. So we need potentially to use, noise models to compensate for that. But also, it is important that we actually then train and test the models using real data, real world data. And in fact, we call this transfer learning, and basically we need to develop techniques exactly to adjust for the real world. I wonder if somebody else would like to add comments about this question.
I can chime in. I think I totally agree with Carla. I mean, this whole idea of transfer learning is really important when dealing with both simulated and experimental data. Just some other points. I mean, there's notions of surrogate modeling and how you go about doing, for example, Bayesian calibration of computer models via surrogate modeling. Because I noticed the question was asking about uncertainty as well. I think this whole idea of multi-fidelity models as well plays into this. I mean, and that's just an entire field of how to deal with this type of heterogeneous data.
Great. Okay. Thank you, Chris and Carla. So our next question is from Erica and Dolores. I'll actually sort of combine these two of his questions here. So given atomic information of crystal structures, how do you use machine learning to work with it, considering that atomic sites are sparse data? And then how do you encode the law of physics for matrix factorization besides asking non-negativity? And so, I think this gets into data density and data topology. And so, Carla, I wonder if you'd be willing to respond to that question.
Mm-hmm. Eric, again, excellent question. And indeed, especially the phase mapping problem is really a great example of what we call unsupervised learning. Unsupervised learning because we don't really have a lot of examples. And, the way you actually have a very specific question is, how do you combine which, did you delete the question already? Oh, okay. Yes, sorry. But how do you actually include physics constraints besides non-negativity? And we actually do that in different ways. In fact, we actually have a few papers on that where we use non-negative matrix factorization. In fact, we use convoluted NMF, and the convoluted NMF is a very nice way for us to, impose constraints with respect to the shifting. But, the solutions that are produced are not guaranteed to be physically meaningful. Therefore, we actually interleaved. In fact, we have a solver called interleaves agile factor decomposition, where we interleaved convolutive NMF with modules, engines that are enforcing the constraints. For example, that are enforcing the Gibbs phase rule or the connectivity constraint. And so we do what we call the relaxation, where we run the convolutive NMF in a relaxed way, in the sense that it's just enforcing the shifting constraints and non-negativity constraints, and we combine this with very specialized and very fast solvers that are going to interleave other constraints and pass again to the NMF solver. So we have this interleaved cycle, to enforce all the constraints. And in fact, for example, phase mapper, you saw the demonstration. Phase mapper typically can produce a physically meaningful solution in less than 3 minutes, using this interleaved approach, combining, convolutive NMF with specialized solvers that are enforcing other constraints.
Great. Okay. Thanks, Carla. So I think what we'll do for this this question and answer segment is ask one more question, and then we'll move on to the last pre-recorded talk. And so this one is from Vignesh Babu Rao, who asks how to choose a particular model or algorithm for my problem. So that's a very interesting question, right? There's a lot of different algorithms or models that you could choose. How do you start to pick one out of all the different possibilities that are out there? So I don't know, Carla, if you want to start on that one.
Well, that is an open-ended question and very, very challenging, actually. It really depends on the characteristics of your problems. For example, are we talking about an unsupervised learning or supervised learning? Meaning, do you actually have data? You may have a lot of data, but do you have examples? So this is immediately, if you don't have examples, that means that, deep learning is not going to work for you. So that you will have to use, what we call unsupervised learning techniques. If you have lots and lots of examples, then you definitely should use deep learning. Then, obviously there are many issues. How can you enforce constraints and interpretability? And, again, there you can use different techniques. And again, I'm here emphasizing essentially machine learning techniques, but, there are many other approaches. And even problems that you can address using AI, how to design experiments, how to plan experiments, and how to, bring together different heterogeneous data sets. So, there are many possibilities. Perhaps just in terms of machine learning, I would say, a key dichotomy is unsupervised learning and unsupervised learning. You are going to use, there are several techniques, clustering techniques or dimensionality reduction techniques, etc. And then if you have examples, again, you have deep learning, you have decision trees, and one challenge about deep learning is how to train the models. For example, decision trees are very, very easy to use, and they don't require a lot of training. And in fact, I think that's why a lot of people they use decision trees. So I wonder if somebody else would like to add some comments.
Sure. I can jump in, or Chris can. Chris, do you want to go first?
No, I think that's good. I think Carl hit on all the major things I was going to say anyway. So.
Sure. As the sort of experimentalist of the group, I've found the hardest part oftentimes is getting a sufficient descriptor set of your material that you can then feed to the machine. And once I have a descriptor set, oftentimes I find that it's best to start with something like Weka or scikit-learn and start with the simplest possible AI algorithms. Mm-hmm. Baseline, naive Bayes, decision tree. Decision tree is nice because it's human interpretable when you're done. Mm-hmm. Random forest, and then start rambling down deeper and deeper as I'm not getting solutions to my liking.
Great. Okay, thanks, Jay. Appreciate it. Carla, just one quick question from Rachel. Is FaseMapper going to be available outside of your group there?
Yes, that is a great question, and the answer is yes. We are, going to make it available, and in fact, we encourage, usage of FaceMapper. That's the point. In fact, I have to say that all my career, I have, all the solvers that I have developed are completely open source and fully available, and will definitely
wonderful
the FaceMapper.
Okay. Great. Thanks to Rachel Solinsky for that question. And Carla, thank you again for a wonderful talk and question and answer session.
May I just...
and I guess, please.
May I just please email me if you want to use FaceMapper.
All right. Thank you. And I guess we'll get your email out there as part of the reference material. And I guess just by way of transitioning to our last recorded speaker, one of the wonderful things about the collaborations here within the group and in my experiences is just working with people like Chris and Carla who are doing computer science and deep data analysis, is that collaboration and really starting to learn one another's language and familiarize one another with the problems that we face in our different domains. And so it's actually very enriching in my experience, and I think probably the other speakers would share that. In this talk, the fact that Carla is working with material scientists is just very motivating.